We start with this is the last refereed paper of the program, and the more astute among you will notice that it's not what it said, because there was a swap with Bruno, who had to be yesterday. This is a short paper. Martin Kleppmann is here from the computer lab, strengthening public authentication.
Thank you very much. Good morning, everyone. Yay! It's a response. Yay! Cool.
Good morning!
Very good. Thank you for coming to the building where I work. So I work here at the computer lab, and I'd like to talk about public key authentication. And so we've talked a lot about password authentication, and we kind of think that passwords are the only thing that people use to authenticate. In reality, I'd like to remind you that there are a few small niches in which other alternative methods actually are used in practice as well. Like, for example, take SSH, which you can authenticate with a password, but actually it's quite common to have a key file in your home directory which you use to authenticate with a server. And as you probably know, the way that works is when you set up an SSH connection, it first does some key exchange stuff and sets up an encrypted channel. And once it's done that, a signature is passed from the client to the server. And that's what authenticates you. And the way that works is that it takes the session ID, which is a kind of unique key that's derived from the handshake protocol, and it signs that on the client using your private key. And the server already knows your public key, and so it can verify the signature. It can check that this is a valid signature for the private key, and thus you prove the ownership of your private key without actually ever giving the private key to anyone. And you know, lots of people use this every day without even thinking about it, but this is essentially what's going on if you log into a server. Similarly, we get a similar thing happening with TLS if you use client certificates. That's not quite as widely used, but in a few kind of little domains. I believe in Estonia, a lot of government services are authenticated with client certificates, for example. And the principle how that works is actually kind of similar again. So you have some kind of handshake through which an encrypted channel gets set up, and then a signature gets passed from the client to the server. And in this case, the thing that gets signed is actually the messages of the TLS handshake. And it passes that signature, and along with it, it passes the public key and the certificate. And so the reason for the certificate there is actually only because the server doesn't know the public key for all of the users up front, so it trusts the certificate authority to do that, that binding of user IDs, user identifiers, to public keys. But then the signature verification actually happens in exactly the same way. And we can continue this further. So these FIDO little authenticator devices are getting quite popular, especially in some enterprises. I quite like these for like two-factor authentication. And how they work is, again, a very similar principle. In this case, it's a kind of challenge response protocol. And you've got a private key that's stored either on this little token itself or kind of encrypted on the server through a slightly convoluted protocol. But the basic principle of this protocol is, once again, you get a challenge from the server. That challenge is signed using the private key and handed over to the server, and the server can check that signature. So all of these three methods are all examples of using public key authentication, and it does actually work really nicely in practice. But the big problem with all of these schemes is, well, somewhere you've got to store a private key, and that private key can get stolen. So it could get stolen through many different ways, like it might be that someone gets hold of the attacker gets hold of the physical device containing the private key and manages to extract it. Maybe they do some social engineering and convince you to send your private key file to the attacker by email. Maybe they manage to get a backup of your device, whatever. So through some mechanism, whatever, this private key material might be stolen. It's especially vulnerable if it's stored simply on the file system on a general purpose device, but even if it's a hardware device, you can imagine somebody just nicking the hardware device. So some kind of extra protection is necessary, and the standard way that this is done is you have some kind of password or passphrase which encrypts that private key, or rather you derive some kind of symmetric encryption key from a password or passphrase, put it ideally through some slow key generation function, key derivation function, and then you can decrypt the key using that. And so people use PBKDF or bcrypt or scrypt, or you could use argon2 or the Katina or the other hash functions we talked about, all kind of as ways to slow down an attacker. So if an attacker manages to get hold of this key material, to what extent can we slow them down simply by making the computation sufficiently expensive that they probably won't be able to break the passphrase in some amount of time? But this is a bit unsatisfying, I find, because basically we're just bounding the attacker by computational resources, and essentially you're looking at the ratio of computational resources of your own device to those of the attacker. And if the attacker is willing to spend some money, that ratio can be pretty high. So you simply can't make the local computation too expensive, otherwise it'll take too long on the local device. So it'd be nice to be able to protect this secret material a bit better. And so I'd like to talk about two ways of doing this. The first one is simply a way of enabling revocation of keys in an instantaneous manner, so that if somebody loses their device, they can revoke it, perhaps using some other device, and thus get assurance that at least the time that the attacker has to break whatever protection is on the key is only the time between the key being stolen and it being revoked. So that limits the amount of time during which the secret is exposed. And then the second thing I'd like to do is to talk about actually rate limiting the password guesses from an attacker other than just by using a slow hash function. So the first of these techniques is a paper from Dan Bonnet and his collaborators from 2001. I haven't seen it much implemented in practice, actually, but it's kind of mildly cited. And the second part of this is our contribution. So this is specific to RSA. I believe it's possible to do something similar with elliptic curves, but I'm just going to talk about RSA only for now. And so I need to do a little bit of maths, but it's very lightweight maths. Hopefully not too much for this time of morning. So if you remember how RSA works, a private key and a public key each consist of two numbers. They share one number, n, which is called the modulus. That's this product of two primes thing that you may vaguely remember. And then there is a private exponent and a public exponent. And the private exponent is what makes the private key, and the public exponent can be known by anyone. And if you want to calculate an RSA signature, the way that works is there's some bit string that you want to sign, which I call stuff here. And you want to sign that with some private key. The way RSA does that is you first take some hash of that stuff, and then you pad it a bit. And then you do a modular exponentiation. So that is, you take that hash which you got, which is some big number, and take it to the power of d, the private exponent, and do that mod n, which is the modulus, which is known. And the result of that is some number that you can then pass around, and that is your signature. Now there's something interesting we can do here, which is we can take that private exponent, d, and we can split it in two. And we split it such that the two components sum to the original exponent, d. And the way we can do that is to pick, say, dA, which is drawn from a uniform distribution between 0 and d. So that's just a uniformly distributed random number. And then dB is just d minus dA. So that way we split the key into two halves now. And now if you insert that back into the signature formula, now you've got you're calculating the hash, and it's something to the power dA plus dB. And if you remember your maths, you can actually reform this and actually turn that into two separate exponentiations. So the sum in the exponent becomes a product when you split it out. And so you've got independently the hash to the power dA times the hash to the power dB mod n. And this way you can actually, once you've split the key, you can construct an RSA signature without ever having to assemble all of the key material in one place. So you can do different parts of the computation in different places, and then just bring them together, multiply them together, and you get a valid signature out at the end. This is kind of interesting. This is called mediated RSA, and this is what Bonnet et al. Proposed in 2001. The reason it's called mediated RSA is if you think about the setup, how this thing can be deployed, normally we have the client and the server, but now we're going to introduce a third component called the mediator, hence mediated RSA. And we're now going to split the key material such that we put, say, DA on the client and DB on the mediator. And so neither the client nor the mediator is able to construct a signature by itself. The two have to work together in order to construct a valid signature. And the way the protocol works is like this now. So say there's, again, some stuff that you want to sign. The client can first calculate the hash of that and do the padding, and it gets a number M. And it's now going to send that number M to the mediator, and the mediator is going to perform its part of the exponentiation using its DB. So it doesn't need to give out the DB to anyone else. It only performs M to the power DB mod N and passes that back to the client. The client can now do its part of the exponentiation. It has DA, so it can do M to the power DA, multiply that together with the result that it got back from the mediator, mod N, and it's constructed a valid signature. And then that signature it can pass to the server, and this can be used in any of these signature-based protocols. So whether this is FIDO or TLS client certificates or SSH, because they basically all use the same, at least if you're using them in RSA mode, they use essentially this signature scheme. This actually works. You can construct the signature, and the server doesn't even realize that the signature was constructed through this mediated protocol. Now, I said I was going to talk about revocation. So the interesting thing you can do now, once you've split the key across these different devices, is now say the client gets stolen, and its key fragment, DA, is now in the hands of an attacker. What the client now needs to do somehow is to make sure that the mediator deletes its counterpart of this key. And the assertion here is that if that DB no longer exists anywhere in the world, then this DA is useless. Because if you simply do M to the power DA for some M, it's just some number. It doesn't tell you anything. You can't use it for anything unless you also know DB. So this is quite a useful property, but there are a few holes in this argument so far. And in particular, we don't know exactly, like, how does the process of getting something from the mediator deleted work? Like, how does the client actually request the mediator to delete something? In the original paper, it seems to be assumed that there's some kind of out-of-band process for doing this, so that the user can go with their password to the mediator service and say, hello, I am the true user, can you please delete my key fragment? Which is okay, but it's not really viable for kind of consumer internet purposes. So we need some way of authenticating requests to the mediator, especially if those requests are deletions. But actually, even for signing requests, it's useful to authenticate them. And then the other thing was rate limiting would be very nice here. So the moment that some key fragment is stolen, a race begins. And now there's a race between the attacker and the genuine user. If the genuine user is first to revoke the key, then they've won, because the attacker can't do anything. Even if they subsequently break the encryption of the fragment that they stole, they can't do anything with it. So the user wants to get to the point of revoking the key as quickly as possible, while the attacker at the same time is trying to break the encryption on this key fragment as quickly as possible. So you've got this race between the two. And so anything we can do to slow down the attacker here is going to be an advantage to the user, because it gives them more time to revoke the key. And now, well, as we said, we can use a slow hash function to slow them down, but there are other things we can do as well. So let's talk first about the authentication of requests to the mediator. And that is, so we've got this three-party setup again, and as before, we're going to calculate M, which is the hash of the stuff we want to sign. But now to authenticate the request to the mediator, it's not only going to send M to the mediator, but also a hash of M to the power DA, mod N. So this can be any hash function now, as long as we trust that hash function to not be reversible. And what the mediator does now is it doesn't just simply take M to the DA, M to the DB, and send it back, it first checks this hash to the power dA acts as an authenticator for that particular request. Because now the mediator can actually use its own DB and calculate the hash of the message that came in using the same hash function and do it to the power dB and check whether what it constructs there is a valid signature for the user's public key. And so if it is a valid signature, then the user has proved that they know the correct DA without giving anyone DA. But if this does not construct a valid signature, then the mediator just says, no, sorry, I'm not going to do any signing for you. And note here also that this doesn't actually give the mediator permission to log into anything, because the signature it constructed is a hash of m. The signature that it needs to log into the server is actually m to the power d, whereas the signature it's constructed here is hash of m to the power d. So this signature that is constructed is a valid signature, but it doesn't help it log into any service at all. And now, once the mediator has validated that this is a valid signature, then it will calculate the m to the power dB mod n, return that back to the client, and the client can now do the same thing as before. It can construct a valid signature and use that to log into the service. Okay, so that's how we can authenticate requests to the mediator. But coming back to this, we have this race here between the genuine user who wants to revoke the key and the attacker who's trying to break the encryption. So we're going to assume now that the private key material on a device is encrypted with a password, or rather a key derived from a password. And so the standard way of doing that would be to use some slow key derivation function. I've put scrypt here. Feel free to substitute with argon2 or whatever you like. And then use some symmetric cipher, probably an authenticated cipher, in order to then take the key fragment, DA, and encrypt it and store that locally. But as I said, the only thing limiting the attacker here is their computational ability. So I'm going to propose an alternative scheme. And the difference here is going to be that, note that if you have an encryption scheme like this, like GCM, for example, it has an authentication tag in it. And the purpose of that is to tell you whether you have the right encryption key without actually going through the decryption process. And so that's a way of preventing padding oral attacks and such like. But what we want to do here actually is a bit different, because in this case, the MAC or the authenticator on the encryption is a way that helps the attacker tell whether password guess is correct or not. Because they can guess a password and check, do I get the right checksum for the encryption key that I derive from the password? And if no, okay, well, try the next one. So this is exactly what an attacker needs in order to do an offline attack. So instead, we can use an encryption scheme that does not have a MAC. So does not authenticate the encryption, which is normally something you would not do because it can be dangerous in various ways. But in this case, it actually is desirable. So in this case, you would still use a slow hash function by all means. But you just put that into something like counter mode, AES, which gives you a key stream of bits. And so this is just some kind of random looking sequence of bits that is derived from the password. And you can XOR that with the key fragments that you want to encrypt. And you encode the key fragment in as many bits as your RSA key is big, say 2048 bits, for example. So the output of this encrypted key fragment, again, is just 2048 bits, because you've XORed one bit at a time. And now an attacker who's stolen this encrypted fragment, the attacker is going to go and guess some kind of password, say pass prime is their guess, and they're just going to run this function in reverse. And they get then some guess of the key fragment, DA prime. And now if their guess of password is correct, then DA prime is going to equal DA, and so in that case, they can break the scheme. But the key thing that an attacker needs to do here is to have some way of telling whether their guess is correct or not. And what we can do now is observe that if the password is correct, the way we constructed this key fragment, dA, is that we drew it from a uniform distribution, somewhere between 0 and d. Whereas now, if the password is not correct, what we get out is a 2048-bit random bit string with no kind of authentication telling it whether this guess of the password was correct or not. So what it looks like is a uniformly distributed random number between 0 and 2 to the k. So in both cases, the output of the decryption is some kind of uniformly distributed random number, except the distribution is not exactly the same. So the only difference you can tell here is that there's a difference in distribution between the correctly decrypted key fragment and the incorrectly decrypted fragment because you guessed the wrong password. And well, I wanted to study this a little bit more detailed, so I just generated 50,000 RSA keys and had a look at the distributions that come out, and found that they do look somewhat similar, these two. Somewhat similar being a very precise cryptographic term, of course. In particular, you could put a bit of experimental data in the paper, but the highlight, like the high-level summary, is that if you look at the entropy of the correct key fragments, the entropy is almost as big as the entropy of a completely random bit string. So you've lost about 1 bit of entropy by encoding this key fragment in a 2048-bit number. And so the practical effect of this is, say you try a password, you try decrypting the key fragment. If the top bit is 1, it's less likely that your password guess was correct. But you still can't rule it out entirely. But it's at that point, you can use this knowledge to prioritize your password guesses, but you can't rule out password guesses entirely. Because essentially this 1 bit of entropy reduction here means you might have to guess half as many passwords as you would otherwise, but on the whole, you still got a very strong, you're still preserving most of the entropy in the password this way. So that's really the whole idea that I wanted to present. The general principle here is you've got some attacker, they've stolen an encrypted key fragment. The key fragment is encrypted with a passphrase, a password that they don't know, but they can try to offline attack. And so they can try to guess this DA. But the key thing here is that just by looking at the decrypted fragment, the attacker cannot tell whether the password was correct or not. They can kind of probabilistically think this is less likely to be correct or more likely to be correct, but it's not a definite yes or no. And so in order to tell for definite whether the password guess was correct or not, the attacker has to contact the mediator and has to perform one of these authenticated requests to the mediator. And this gives the mediator an opportunity to rate limit those requests. Because if the mediator gets an incoming signature with an incorrect, if this DA prime here is not correct, then the result is not going to be a valid RSA signature, so it's just going to say no. And so the attacker then learns the fact that that particular password was incorrect, but it doesn't learn anything else that would help it break the scheme in other ways. So it still has to make a request to the mediator for every single password guess. And this allows the mediator to perform rate limiting then. And it can say that after some number of guesses, it's going to restrict your guesses to 1 guess every 10 seconds. And then even if you have a pretty weak password, it's actually still going to give the user a really long time to revoke the key. That's really all I wanted to talk about. So that's the general scheme of the system that we said. If you want to see more detail, I've put the paper here at martinkl.com/pass15. The idea of MRSA, this mediated RSA, was just stolen from this top paper on the list here. Hopefully I still have a few more minutes for questions. Thank you.